Welcome to the deep dive. Today, we're going to dive into affective computing and specifically how researchers are using brain activity to recognize emotions
Yeah, it's almost like mind reading, but with EEGs.
with EEGs. I know for students in the creative robotics course, this is super relevant because if you're trying to create truly interactive and responsive robots, they kind of need to understand human emotions.
Exactly. Yeah, and it's like taking human-computer interaction to a whole new level.
Yeah, but before we get too far ahead of ourselves, um, what exactly is affective computing?
Affective computing, it's this multidisciplinary field that combines computer science, engineering, psychology, and even neuroscience to create systems that can understand, interpret, and even respond to human emotion.
Okay, so imagine a world where computers can sense your frustration
Right?
and offer help, or robots can react to your joy with empathy.
Yeah, like a more natural interaction.
That paints a pretty cool picture. But why is emotion recognition so crucial for human-computer interaction?
I mean, think about how often we misunderstand each other as humans.
Yeah.
A lot of it comes down to not understanding each other's emotional states. Now imagine trying to interact with a machine that has no clue how you're feeling. It's just going to be awkward. Right.
Yeah, it makes a lot of sense.
Yeah.
So it's not just about making machines smarter, it's about making them more in tune with us, like on an emotional level.
Yeah.
But emotions are these really intangible things. How do researchers even begin to model and measure them?
Well, there's a couple of ways. One is to use what are called discrete emotion models, which are basically just categories of emotions.
Like happy, sad, angry.
Exactly. Happy, sad, angry, disgusted,
So
surprised.
like the emoji keyboard we use all the time.
Exactly.
Okay, I can see how that's kind of a simple way to start.
Yeah.
But it does seem a little limiting, like
Yeah.
trying to shove all the complexity of human emotion into a couple of little icons.
Yeah, you're totally right. And that's where dimensional emotion models come in.
Okay, dimensional emotion models, what are those?
So these models represent emotions more as points in a multidimensional space, which allows for more like subtle representations of those emotions.
Okay, so tell me more about these dimensional models. How do they actually work?
The most common one is the valence arousal model.
Valence arousal.
Yeah, so valence refers to kind of how positive or negative an emotion is. So like happy would be positive, sad would be negative. And then arousal is more about the intensity or energy level of the emotion. So like if you're ecstatic, you're high arousal, but if you're just content, you might be low arousal, but still positive.
That's a really interesting way to think about it. It's like plotting emotions on a map, with each emotion having its own unique coordinates.
Yeah, exactly.
But we've got all these different models for emotions now. How do we actually capture the signals? Like, where do we even look?
So there's kind of two main approaches. One is to look at behavioral cues, so things like facial expressions, body language, speech patterns. But the problem with those is they can be faked.
Right, like when you try to keep a poker face even though you're dying inside.
Exactly. And so that's where physiological signals come in.
Okay, physiological signals.
So these offer a more direct window into our emotional state because things like heart rate,
Okay.
skin conductance, think lie detectors,
Yeah.
respiration, all of those are influenced by emotions but are a lot harder to control consciously.
Okay, so we've got behavioral cues, we've got physiological signals, but you're telling me there's an even more direct way to measure emotions, like tapping into the brain activity itself.
Yeah, and that's where BCIs come in, brain-computer interfaces.
Okay, BCIs.
And when it comes to effective BCIs, one of the most common techniques used is EEG, or electroencephalography.
EEG, okay, that's the one with all the electrodes on the scalp, right?
Yeah.
It sounds kind of intimidating.
No, it's non-invasive. You don't need any surgery. It's basically just these electrodes measure electrical activity in your brain.
And somehow that tells us about your emotional state.
Well, different regions of the brain are associated with different functions, and some of those are emotion processing.
So by measuring these tiny electrical signals, we can decode what someone is feeling. How does that even work?
By analyzing the patterns coming from those regions, we can sort of get a glimpse into their emotional experience. Of course, it's not really mind reading. It's more like recognizing patterns in a complex electrical symphony.
A symphony, that's a great analogy. But I can imagine there's a lot of challenges involved in collecting and interpreting EEG data.
Mm.
What are some of the biggest hurdles that researchers face?
One of the biggest ones is just how noisy EEG signals are.
Noisy.
You have interference from muscle movements. Even little tiny things like blinking or slight twitches can create artifacts in the data. And then there's all the electrical activity from the environment, too.
So it's almost like you're trying to listen to a whisper in a really crowded room.
Exactly.
Yeah, that's a tough one. So all that mental chatter and physical fidgeting can really mess with the readings.
Yeah, definitely. That's why data preprocessing is so important. Researchers use all these sophisticated techniques to clean up the data and try to isolate the brain signals related to emotions.
It's like sifting through static to find the clear signal. So we've got noise to contend with. What else makes EEG data for emotion recognition such a challenge?
Well, another big one is that every brain is different.
Ah, the one-size-fits-all dilemma.
Yeah, so even if you manage to decode someone's emotions perfectly, that same algorithm might not work for someone else.
So it's like trying to create a universal language translator when everyone speaks with a slightly different accent.
Exactly. Yeah, it's a challenge.
Sounds like working with EEG data for emotion recognition is a real balancing act. You've got to find that signal amidst all the noise, account for individual differences, and then somehow translate all of those electrical patterns into meaningful emotional insights.
It definitely is. But despite all those challenges, researchers are making some incredible strides in the field, and I'm excited to dive into some of those advancements with you.
I'm all ears. Let's get to it.
Welcome back to the deep dive. Before the break, we were talking about some of the challenges of using EEG for emotion recognition. But despite those hurdles, there have been some remarkable advancements.
Okay, I'm ready for some good news. What kind of progress are researchers making?
Well, one really exciting area is the development of more sophisticated algorithms for analyzing EEG data.
Okay.
Traditionally, researchers relied on what were called handcrafted features, which basically meant they had to manually select specific aspects of the EEG signal that they thought were relevant to emotions.
So they were essentially trying to pick out the emotional needles from the haystack of brainwave data one by one.
Yeah, pretty much. And it was really time-consuming and prone to bias.
Sounds tedious.
It was. But now, thanks to advances in machine learning, we're seeing a shift towards automated feature extraction. So algorithms, particularly deep learning models, can learn to identify relevant features from the raw EEG data directly.
Deep learning models, those are the rock stars of the AI world, right? The ones that can recognize faces and objects in images.
Exactly, yeah. And now they're being applied to brainwave data with some pretty impressive results.
Oh, wow.
These algorithms can sift through massive amounts of data, identifying those subtle patterns and relationships that humans might miss. It's like having a superpowered detective for emotion recognition.
That's fascinating. So by leveraging the power of these advanced algorithms, are researchers able to overcome some of those challenges we talked about earlier, like the noise and the individual variability?
To a certain extent, yes. These algorithms can learn to filter out that